Hello boys and girls, welcome back to Direct3D 12 Shallow Dive, also known as Chili and the Quest for the Rainbow Dorito. In the last video, we set up our vertex buffer, we loaded our data in there, we got our view set up, and now it's time for us to look at this bullshit. What is this? Okay, what are those? Stuff that you have not seen before in Direct3D 11. But it might look familiar to the discerning eye. So what do we know from Direct3D 11? Well, we know that to draw some geometry, we basically have to bind a bunch of things to the pipeline, configure the pipeline, setting up things like the pixel shader, the vertex shader, scissor, viewport, setting up your vertices, what's the topology, all that stuff. You set it all up, and then at the very end you call your draw, and rendering happens. And the thing that you call all these commands on is your immediate context. Now, we don't have our immediate context in Direct3D 12 anymore. It's gone. What we do have is a command list. So we are going to do the same kinds of setting things, but we're going to call them on the command list. Stuff like, setting up your scissor rectangle, binding your vertex buffer. But some of those things, like the pixel shader and the vertex shader, you don't call them on the command list. What you do is you actually configure something called a pipeline state object. And you set up what's the pixel shader, the vertex shader, and you set all these things up, and then you basically compile a pipeline state object. And then you write a command to bind that pipeline state object to the pipeline to configure it. So you no longer have individual functions for I just want to change the pixel shader, I just want to change the vertex shader. If you want to have the same setup except change one of the shaders, you have to basically build a new pipeline state object, compile it, and bind it to the pipeline. And it might seem worse, but this is actually what was really happening behind the scenes with Direct3D 11, only the driver was taking care of that. So when you changed one of these things, it would have to, rebuild the pipeline state object. Maybe it would cache, different iterations of it or whatever, but it was all hidden from you. You couldn't control it. And sometimes it would do things that were not optimal because it wasn't aware of, your exact use case. The driver wasn't. So now you build your pipeline state objects explicitly and you manage them as you will. Now the last thing here, a root signature. So what the heck is that? Another weird thing that we have to bind to the pipeline? Well, if you look at the things that go into it, they all share something in common. These are all things that are accessed primarily from shaders. That's what the root signature does. It exposes resources, textures, constant buffers, that sort of thing, samplers, to the shaders. And so you set this thing up, you compile it, kind of like the pipeline state object, and then you bind it to the pipeline. It also is required to create the pipeline state object. It needs the root signature in order to do some validation to make sure that these things match up. And once you create a pipeline state object based on a root signature, you can only ever use a pipeline state object with that exact root signature. So you could have multiple pipeline state objects that match one root signature and switch them out, but you can't keep your pipeline state object and then switch out a root signature. That's never going to fly. But this root signature stuff is not important for us right now because we're not going to have any constants, any textures or anything like that. We're just drawing a rainbow Dorito. So we're going to be happy with an empty root signature, but we still have to create one and bind it. It is mandatory, even if it's empty. So we create our COM pointer to hold the root signature. Let's define the root signature. The first step to defining is, of course, you need a descriptor. You always need your desc. We got a nice XBoy here to help us out. It's got a init function that's going to set things up for it nice. Now the init function, what does it take? Let's take a look at this here. So it takes a number of parameters and then a pointer to an array of root parameters. And this is the place where you would configure and put in all the things that the root signature is exposing to the shaders. But of course, since we have nothing in there, it's 0 and no pointer. And it's ditto for these ones here. These ones are for samplers. So this is where you would put your list of samplers that you want to be exposed. And here, finally, we have a collection of flags. You can combine flags for the root signature. There's one that we need to have, and that is allow input shader or input assembler input layout. So yeah, because we have an input layout, or we will have an input layout for our vertices, we need to enable that. So that's important. Now the next thing we want to do is serialize the root signature. So it starts off, we define it in a structured format that is defined by Direct3D 12. We need to serialize that into like a stream that is a format that drivers will understand. You can kind of think of this like compiling a shader from HLSL to the intermediate language, DXIL. But for root signatures. So what do we do here? Well, I mean, I want to do some logging here. So let's include chillog stuff. In here, I'm going to include logging and also my string utilities so I can go wide to narrow. We serialize the root signature, pass in the descriptor, version of the root signature. We'll use version 1. It's a little simpler to set up. But for realsies, you'd probably want to use version 1.1. It's a little more efficient. We'll maybe look at that sometime in the future. And then, yeah, when you're done, it's going to fill up a blob of just binary data similar to what you do when you compile a shader. And if something went wrong, it's going to fill this blob with some text, I guess. Now, because we have this text in the error code, that means I can't really use my check directly because I want to also spit out this error information if it exists. So if something goes wrong, I check my HR in an if statement. And if something goes wrong, I see if I got anything in my error blob. And if so, I'm going to output that to chillog. And then I will pipe my HR into check, which will throw an exception. So there you go. Serialize the root signature. This puts it in a format. It's still in a standardized format, but it's in a standardized format that the drivers will like to consume. So once we got it in that format, then we are going to actually create the root signature. It's just call to the device, which is very common when you are, creating some kind of resource on the GPU side, but a driver. So we pass it the serialized root signature, and the driver is going to turn that into a format that is specific to that hardware. So this allows freedom. It's not one format for all different vendors. Every vendor, NVIDIA, Intel, AMD, they can all specify their own formats for their own optimization. It's opaque to us now. All we do is we get back now this handle to the root signature that we can now bind to the pipeline. I wonder what this is. What's this 0 in here? Node mask. So this is for setting for different GPUs. Oh, fair enough. Not something that we're ever going to touch. It's always going to be 0. Okay, so now we have the root signature. It's fairly simple to create an empty one. It will be more complicated when we start binding stuff to our shaders. Now we get to the most complex part of this whole ordeal, the pipeline state object. So it's kind of similar to a root signature in that it needs to be kind of compiled by the driver in its own specialized format. So we describe it and then we stream it out and it gets compiled. Of course, it has its own bespoke interface for COM. Now, the way that you describe a pipeline state object is quite unique. So the description of a pipeline state object is a stream of bytes, but the typical way to make that stream is by creating a struct. And that's interesting. So when you think of struct, you think it's got a static fixed size, and there's a definition of the struct that, both the API and the calling code understand. All the bytes are in the same order. But with this struct, it's free form. Like I could take this line here, I could move it up to the top, and it would still work. It would still be parsed fine by the API. And you might be wondering, how is that possible? Well, the thing about this structure here is we're using D3D X members. Each one of these members here is itself a structure with 2 members. And the first member is like an enumeration. It's an int value. And that int value tells you what the second member is. Tells the Direct3D API, okay, so there's going to be a root signature. It'll know the size, and then it'll read the bytes. And then after it reads the root signature data, it will expect another integer to tell it what the next thing is. It'll look at that integer and it'll say, this is an input layout, and it'll read the data for input layout. And it does the same thing. So this structure, this pipeline state stream, it's actually an interleaving of integer values and then some kind of arbitrary data, and then another integer and then data. And there's some tricky things about that, because think about it this way. If your packing is wrong on your data, the way that the API reads is going to be misaligned and everything is going to blow up. So you have to make sure that you have the correct packing, and you have to make sure that you do it in the correct order. Number, and then structure, and then number, and then structure, number, data, number, data. And if you mess that up, it's going to blow up and it's going to be hard to debug. So what D3DX does for you is it gives you these pipeline state stream things that pack it all up very nice for you. So it's based on this template, it seems here. Pipeline state stream sub-object. Go to definition of that template. And you can see it has two members. The type member, which is just an enumeration, just an integer value, and then the actual data structure, which is differing sizes depending on what it is. But there's some beautiful things going on here with this template. Like, for example, they put align as void pointer. So that means that you're not going to have weird packing that messes up your data alignment so that the stream goes out of sync when it's being read by Direct3D. Takes care of the alignment for you. It makes sure that you always have a type and a structure paired together in the correct order. So this D3DX stuff makes creating these pipeline state streams a lot less painful. They also define nice constructors where you can just assign like the payload data to it and it will set it up in the correct place in the structure. So very cool. Maybe that description was a little deeper than what I should be doing for my shallow dive, but I think it's worthwhile to have a little bit of an understanding of how this stuff works. But the main takeaway here is that you create the structure, you put in these D3DX members, and they correspond to the things that you want to set up in your pipeline. So we need a vertex shader and a pixel shader. We need to set up our render target view format. Note that this does not specify which render target we are going to be using. It just says, okay, any render target that we bind has to have this format. We set up our topology, which is like triangle, line, point, whatever. Input layout, very important. That's the layout of our vertices. And what root signature that we're going to be using. So like I said in this diagram, when you create your PSO, you've got to tell it what root signature is going to be used with that PSO. So this is how we define the stream, where we're going to set all those things. So clearly we're going to need an input layout to set on this stream. And this is just the exact same stuff as D3D11. I'm pretty sure you could like replace this 2 with a 1 and it would work as long as you have the correct includes. But we need to load our shaders, our vertex shader and our pixel shader. We're going to do compiling just with Visual Studio during our project build, but we need to load it. And technically you don't need this function to load this data. You could do it just with, std fstream, but it's convenient. So I'm going to go up here in our includes and we're going to include D3D Compiler. Now in our input here, we have got to link to it. And that should do it. Just make sure we're on all configurations. Apply that. Okay. So that should make this code happy down here. One problem, these shaders don't actually exist. So we've got to add shaders. And they're just basic shaders. There's nothing different between 11 and 12 and the ones that we're going to create here. So we create our vertex shader, pixel shader, HLSL, and it's your basic thing. You take in the stuff from our vertices, you copy that out to the output structure, SV position, and then in pixel shader, we're just forwarding the color to the render target. So I shouldn't need to explain this for, the audience that I'm targeting in this series, but there you have it. One thing that we do have to do, don't forget, just set this type of our shaders. We're going to use shader model 5.1 pixel shader, and we do the same sort of thing for our vertex shader. And there you go. So now we have the things that we need all set up. Now we actually have to fill in the data for this pipeline state stream. And this stuff should be pretty, self-explanatory. Again, we can assign directly the kinds of data that each one of these state stream objects requires due to the magic of D3DX. So the pointer to the root signature interface, the input layout is a structure that has a pointer to the layout plus number of elements in the layout. What's our topology type? Triangle. So this thing, the VS and PS, they take a type of, let's take a look here, go to definition. So the data type that is expected here is D3D12 shader bytecode, which is different than the data type of a blob, which is typeless. So it's D3DX12 has a nice shader bytecode structure thing with a constructor that you can use to convert those cleanly. And render target view formats, that's just an array of DXGI formats, and then you tell it the number of things in the array. So easy peasy. Last but not least, we actually have to build the pipeline state object. This is where we pass on the stream to API. It's going to get passed on to the driver, and the driver is going to build its own implementation-specific pipeline state object. Yeah, I've created a descriptor here, which is just pointer to the stream plus the size of the stream, and we pass that into the function. And it's going to fill up our pipeline state, and we're all done. We now have our pipeline all set up. We are almost ready to render. We just need two more things. Very simple, boys. So here they are. We need our scissor rect and we need our viewport. And these ones are, more or less the same as what you're going to get in D3D 11. D3D X12 gives you some nice constructors so you can, pass in fewer options, and all of the stuff you don't care about just gets defaulted to something that is sane. All right, now let's actually set up the pipeline and draw the geometry. So render target view, we now need it to both clear and also to bind to the pipeline. So we should move it out of this scope here. So we'll just move that up here. All right, so after we clear and before we start the process of presenting, we need to set up the pipeline and draw the geometry. These calls are pretty much dirt simple, right? We need to set pipeline state object. We need to set the root signature, those two big boys. We're going to configure the input assembler. We set the primitive topology as triangle list. And you might say, didn't we set that up in the PSO? In the PSO, we said that we were going to be rendering triangles. This sets it up exactly what kind of triangle data. Is it list data? Is it a strip? Does it have adjacency, etc.? And in here, we actually bind the vertex buffer view. Going to set up our trivial rasterizer stuff, the viewports and the scissor rectangle. Then we bind our render target. You can bind multiple render targets, as you probably know, but we're just binding one. So as the array, we just pass in a pointer to our render target view, and we say, yeah, we've got one element in this array. This is just a little bit of an optimization. If your render target view descriptors are all contiguous in memory, then it can save a little bit of dereferencing. But since we only have one, yeah, it is contiguous technically, so we can pass in true in here. And this one here, the null pointer here, is for the depth stencil, which we are not using currently, so we'll just set that to null pointer. And finally, last but not least, we draw the geometry. We are calling draw instanced. There is no draw not instanced. So if you want to draw something that isn't instanced, you just say number of instances is going to be 1. And our offset into the vertices of the instance is 0. How many vertices are we drawing? That's the n vertices that we had, stored previously up there. And there you go. We should now be drawing a triangle on the screen. Let's build. Let's see if this builds first of all. Builds on the first try. Amazing. Let's run it. Click the run button and bam! Graphics error. System cannot find the file specified. Oopsies. Okay, well, let's double click on our nice little thing here. So we are failing to read our CSO file. This is a common issue. People using, especially beginners when they do this, they often come crying in the comments and in the Discord. It's not working. I can't find my files. Well, that is because, okay, so we compiled the pixel shader. It is going to put that data in the build output directory. So it's going to put our CSOs in here with all of our other build output. But by default, in debugging setting here, when you run your program, the working directory, your CWD, that defaults to the project directory, which is where your source files are. So that's not what we want. We want to put this to the outer where our CSO files are. For right now, anyways. We'll think about it later on if we want to change it. But now if I run it, hallelujah! We have reached the Holy Land. We have completed our quest, and the Rainbow Dorito is ours. Praise Harambe. And so there you have it. There's a very minimal drawing, pretty much the most minimal rendering you could come up with almost. And you can see even that requires quite a bit of code. And we're even getting some help from D3DX. It would be more code if we weren't using D3DX. But yeah, this is a good starting point. We're going to build on from here. We're going to be adding things incrementally, and that will allow us to dig deeper into stuff like, for example, root signatures But that's going to be for the next video. I guess in the next video, let's spin our Dorito. That'll be a fun little thing we can try. So in the next video, we will spin our Dorito and maybe also do a little studying on how root signatures work. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. Helps a lot. And I will see you again with some more Shallow Dive.